Today we are going to discuss Chapter 2 Thermodynamics of Physical Chemistry. 2.1 Introduction Need for the second law and different statements of the law. The first law of thermodynamics had certain serious limitations. To overcome these limitations, a strong need was therefore felt to introduce another law called the second law of thermodynamics. A few limitations of the first law and as a consequence some definitions given to the second law are briefly given below. First, a major limitation of the first law of thermodynamics is that it merely indicates that in any process there is an exact equivalence between the various forms of energies involved, but it provides no information concerning the feasibility of the process, that is, whether the process is possible or not. For example, the first law does not indicate whether heat can flow from a cold end to a hot end or not. All that it tells is that if this process occurred, the heat energy gained by one end would be exactly equal to that lost by the another end. Similarly, the first law does not tell whether a gas can diffuse from low pressure to high pressure or water can itself run uphill, etc. The second law supplies answer to above questions by stating that all spontaneous process like the flow of heat from hot end to cold end, diffusion of gas from high pressure to low pressure, or the flow of water down a hill, etc., are thermodynamically irreversible. The term spontaneous process used in the above definition means a process which can take place without the help of any external agency. All natural processes, some of which are mentioned in the definition above, are spontaneous process. However, it may be mentioned here that the term spontaneous does not give any idea of the rate of process, that is, whether the process takes place fast or slowly. All that it implies is that a process can occur without the help of an external energy. The second law states that when heat is converted into work, the work obtained is equivalent to the heat absorbed. However, it has been seen from experience that the heat absorbed cannot be completely converted into work without leaving some change in the system or the surroundings. For example, the heat produced in a locomotive is not fully utilized in running the train. A part of it is lost to the surrounding or wasted in overcoming the friction. Hence, the second law is also stated as follows: the complete conversion of heat into work is impossible without leaving some effect elsewhere. Besides the above definition, number of other definitions have also been given to the second law of thermodynamics. The two important ones are: first, it is impossible to construct a machine functioning in cycles which can convert heat completely into the equivalent amount of work without producing some changes elsewhere. Second, without the use of an external energy, heat cannot be itself passed from a colder to a hotter body. The term functioning in cycle is introduced in the above definition to indicate that the machine must return to its original state at regular intervals so that it can function continuously. Further, it may be recalled that in an isothermal reversible expansion of an ideal gas, where delta U is equal to 0, so that Q is equal to W, that is, the work done is exactly equal to the heat absorbed by the system. In other words, in this process, heat is completely converted into work. However, it is important to observe that this conversion is accompanied by an increase in volume of the gas so that the system has undergone a change. A number of other definitions have also been given to the second law of thermodynamics, which we will come across in the succeeding sections of this chapter. The fraction of heat absorbed by a machine that it can transform into work is called the efficiency of the machine. Thus, if Q is the heat absorbed and W is the work done, then the efficiency of the machine is given by W by Q. The machine used for the conversion of heat into work is called heat engine. In order to bring about this conversion, the engine absorbs heat from a heat reservoir at a higher temperature called the source. Convert a part of it into work and returns the remainder to the heat reservoir at a lower temperature called the sink. Second, Carnot cycle and its efficiency. In order to calculate the efficiency of any heat engine, Sadi Carnot devised a technique called Carnot cycle. A cycle is a process in which a system returns to its original state after a number of successive changes. A process conducted in this manner is called a cyclic process. The engine chosen by Carnot for the purpose of the calculation of efficiency was a hypothetical one and cannot be achieved in actual practice. It was selected because it could be subjected to a simple thermodynamic treatment. It consists of a cylinder containing 1 mole of an ideal gas as the working substance and fitted with weightless, frictionless piston so that all the operations in the cycle are carried out reversibly. For this reason, it is called reversible heat engine. The cylinder is supposed to be insulated on all sides except at the bottom so that heat can flow to or from the system only through the bottom. Further, it is supposed that there are two heat reservoirs, one at a higher temperature T2 and the other at a lower temperature T1. If some operation is carried out by placing the cylinder in the source or the sink, it can exchange heat with it and hence the temperature remains constant so that the process is isothermal. On the other hand, if during an operation the cylinder is placed on an insulating material, no heat exchange can take place between the system and the surrounding and hence the process is adiabatic. The Carnot cycle consists of four different operations which can be represented on a pressure volume diagram. These operations are carried out as shown in the figure 2.2. First is isothermal expansion. The cylinder containing 1 mole of the ideal gas occupying a volume V1 is placed in contact with the source. The gas absorbs heat Q2 from the source and expands isothermally and reversibly till its volume has increased to V2. The path of the process is represented by the isothermal curve AB. Since the gas is ideal, the work done W1 is by 1 mole of the ideal gas will be given by minus W1 is equal to RT2 ln of V2 by V1. Further, for an ideal gas, the work done is equal to the heat absorbed Q2 so that minus W1 is equal to Q2 is equal to RT2 into ln of V2 by V1. Where, hence, W1 has been taken as negative and Q2 as positive by the latest SI conventions of this sign. Second is adiabatic expansion. The cylinder is now removed from the source and placed in a perfectly insulating material so that the gas now expands adiabatically and reversibly. Work is done in the expansion, but since no heat enters or leaves the system, the temperature must fall. The reversible adiabatic expansion is continued till the temperature has fallen to T1, which is the temperature of the sink. Suppose the corresponding volume becomes V3. The path is shown by the adiabatic curve BC. The work done W2 will be given by minus W2 is equal to CV into T1 minus T2 or minus CV into T2 minus T1, where CV is the heat capacity of the ideal gas. Here again W2 is negative by the usual convention of the sign. Third is isothermal compression. The cylinder is now removed from the insulating material and placed in contact with the sink. The gas is compressed isothermally and reversibly till the volume decreases from V3 to V4. The process is represented by the path CD. The work done is taken as positive by the usual convention of sign and hence will be given by W3 is equal to RT1 into ln of V4 by V3. During the operation, an amount of heat Q1 exactly equal to W3 will be returned to the sink at T1, that is, heat has been given out by the system. Using the appropriate convention of sign, Q1 will be negative and W3 will be positive, so that minus Q1 is equal to W3 is equal to RT1 into ln of V4 by V3. Fourth is adiabatic compression. The cylinder is now removed from the sink and placed again on the insulating material. The gas is then compressed adiabatically and reversibly along dA till the initial state A is regained. The temperature of the gas rises from T1 to T2. The work done is positive by the convention of sign and will be given by W4 is equal to Cv into T2 minus T1. As a result of these four operations, the system has returned to its original state so that a reversible cycle has been completed. The net work done by the system will be given by W is equal to minus W1 minus W2 plus W3 plus W4, that is RT2 into ln of V2 by V1 plus RT1 into ln of V4 by V3. Since V1 and V4 lie on one adiabatic curve and V3 and V2 lie on another, it follows that V4 by V1 raised to the power gamma minus 1 is equal to T2 by T1 and V3 by V2 raised to the power gamma minus 1 is equal to T2 by T1. On comparing these equations, we get V4 by V3 is equal to V1 by V2. Putting these values in equation, we get W by Q2 is equal to T2 minus C1 by T2, which gives the efficiency of the Carnot cycle or engine. Carnot theorem. From equation, it is clear that the efficiency of the reversible heat engine depends only upon the temperature of the source and the sink and is independent of the nature of the working substance. Another important observation to be made from the above derivation is that the work done in the cycle is only the one involved in the isothermal operation, because the work done in the adiabatic operation cancel one another. Further, as discussed earlier, the work done in a reversible isothermal expansion is maximum, whereas the work done on a gas during the reversible isothermal compression is minimum. Hence, the total work done by the system is maximum for the specified condition and therefore the efficiency is maximum. The results that follow from the Carnot cycle is called Carnot theorem. It may be stated as follows. The efficiency of a reversible heat engine depends only upon the temperature of the source and the sink and is independent of the nature of the working substance. In other words, all reversible heat engines working between the same two temperatures have the same efficiency. Further, it states that the efficiency of a reversible heat engine is maximum for the given temperatures. Since the quantity T2 minus T1 by T2 is always less than unity, the efficiency of the heat engine is thus always less than unity. In view of the above discussion, the second law of thermodynamics is somewhat defined as follows. A heat engine absorbs a certain amount of heat from the source, converts a part of it into work and returns the rest to the sink. In other words, it is impossible to convert heat completely into work. Further, on combining the equations 2nd, 5th and 8th, we get W is equal to Q2 minus Q1. That is, the net work done by the system is equal to the net heat absorbed by the system. Putting these value of W in equation 13, we get Q2 minus Q1 by Q2 is equal to T2 minus C1 by T2. Hence, the efficiency of a heat engine may be given by any one of the following expression, that is, efficiency is equal to W by Q2 is equal to Q2 minus Q1 by Q2 is equal to T2 minus T1 by T2. That is equation 14. This result derived for a reversible Carnot cycle leads to the introduction of a new thermodynamic term called entropy. Next is thermodynamic scale of temperature. From our earlier studies, we are familiar that a thermometer is constructed most commonly by taking suitable amount of mercury in a glass bulb at the end of a capillary tube and marking 0 when it is placed in contact with ice and marking 100 when it is placed in the boiling water. The length between the 2 points is then divided into 100 equal parts called degrees. The scale of temperature thus obtained is called Celsius scale of temperature. However, because different liquid expand to different extent, that is their coefficients of expansion are different and also they do not expand uniformly over a given range, thermometers constructed by using different liquids will show different numerical value of temperature between their fixed point. For example, a body may show a temperature of 28.7 degrees Celsius with mercury thermometer but may show 28.8 degrees Celsius with an alcohol thermometer. The problem was solved by study of properties of gases. It was found that an ideal gas or a perfect gas ceases to exist at a temperature of minus 273.15 degrees Celsius. This temperature was called 0 degree absolute. The scale developed on this basis is called perfect gas temperature scale and is found to be independent of the ideal gas taken. However, based on the efficiency of a reversible heat engine, Lord Kelvin was the first to develop a scale of temperature that was independent of the nature of gas taken in the heat engine. This scale of temperature is called thermodynamic scale of temperature or Kelvin scale of temperature. It is found to be identical with the ideal gas temperature scale. The basis of the development of this scale is briefly described below. Suppose there are two constant temperature heat reservoirs, one acting as a source and the other as a sink, and a reversible heat engine operates between them. The temperature of each reservoir on the new scale may be taken as proportional to the quantity of heat absorbed from the source and the heat lost to the sink. If Q2 is the heat transfer from the source and Q1 is the heat transfer in the sink, then if their temperatures on the thermodynamic or Kelvin scale are represented by theta 2 and theta 1 respectively, we shall have Q2 by Q1 is equal to theta 2 by theta 1, which is equation 1. Thus, this ratio of two temperature has been defined in a manner independent of the nature of the thermometric substance. Taking the reciprocals of both sides of equation 1 and subtracting the result from unity, we get 1 minus q1 by q2 is equal to 1 minus theta 1 by theta 2. Putting theta 1 is equal to 0, we get q2 minus q1 by q2 is equal to 1. This implies that the 0 on the Kelvin scale is the temperature of the sink for a reversible heat engine whose efficiency is unity, that is, which is capable of converting heat completely into work. But from equation 14, it may be seen that it is possibly only at absolute 0 on the ideal gas scale of temperature. This leads to the conclusion that the Kelvin scale and gas scale are identical, provided the gas is ideal. The temperatures on the thermodynamic scale are therefore expressed in terms of degree Kelvin. Further, it has been found that if the lower fixed temperature is taken as equal to that of triple point of water, that is 273.16 K, then Kelvin is exactly equal to Celsius degree. For this reason, the temperature on the absolute scale in which the melting point of ice is taken as 273.16 degree is often referred to as degrees Kelvin. It may be concluded that thermodynamic scale of temperature as defined on the basis of second law of thermodynamics is more basic than that based on an ideal gas because any fluid can be used. However, the ideal gas scale is more practical for laboratory use. 2.5 Concept of entropy. Entropy as a state function. For a reversible Carnot cycle working between temperatures T1, T2 and T1, it has been seen that Q2 minus Q1 by Q2 is equal to T2 minus T1 by T2, equation 1, where Q2 is the heat absorbed isothermally and reversibly at temperature T2 and Q1 is the heat lost isothermally and reversibly at temperature T1. So the above equation may be simplified as 1 minus q1 by q2 is equal to 1 minus t1 by t2, that is q by t is equal to constant. Thus, we conclude that the heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which the heat is absorbed or lost is a constant quantity for a particular system. Further, in equation 2, Q2 is the heat absorbed at temperature T2 and Q1 is the heat lost at temperature T1. If Q1 were the heat absorbed at temperature T1, then equation 2 would be rewritten as Q2 by T2 is equal to minus Q1 by T1, or summation of Q by T is equal to 0, which is equation 3. Now consider any reversible cycle ABA. It may be regarded as being made up of a number of Carnot cycles drawn across the diagram as shown. Starting from A and going through all the cycles successively from A to B, it can be shown that all paths inside the closed curve ABA cancel each other, leaving only the zigzag path, which is almost the same as the path ABA of the reversible cycle. By making each Carnot cycle smaller and increasing their number, it can be made to correspond more closely to ABA. The reversible cycle can therefore be regarded as being made up of an infinite number of Carnot cycles. For each of these cycles, we have summation q by t is equal to 0. Hence, for an infinite number of Carnot cycles, summation of del q by t is equal to 0, which is equation 4, where del q is a very small quantity of the heat absorbed at temperature T during the small isothermal change of the reversible process. Further, above term may be divided into two parts, one for the path A to B and other for the back path B to A, and thus we can write that q by t from A to B is equal to minus q by t from B to A, which is equation 5. This implies that the total value of the quantity q by t for the path A to B is equal to the total value of quantity q by t for the reverse path B to A. Hence, it may be concluded that the quantity q by t is a state function, that is, its value depends only upon the initial state A and the final state B and is independent of the path. Obviously, q by t is the change in the value of quantity or a function having some definite values at A and B depending upon the values of pressure, volume and temperature. This quantity or the function is called entropy and is usually represented by the symbol S. Thus, if SA is the value of the entropy at A and SP is the value at B, then we must have q by t is equal to delta S, which is equation 6, where delta S represents the total change in entropy in going from the initial state A to the final state B. Hence, entropy may be defined as a state function, the change in the value of which from the initial state to the final state is equal to the quantity q by t, that is, the total heat absorbed reversibly and isothermally in going from the initial state to the final state, divided by the absolute temperature at which the heat is absorbed. From equation 6, the entropy change may be defined directly as the quantity of heat absorbed isothermally and reversibly divided by the absolute temperature T at which the heat is absorbed. It is important to note that as entropy is a state function, therefore the value of entropy change during a process should not depend upon the path, that is, whether the heat is absorbed reversibly or irreversibly during the process. However, since the derivation of above result is based upon Carnot cycle in which the heat is absorbed reversibly, therefore the expression 6 for the entropy change is valid only when the heat is absorbed reversibly. Thus, it is better to use the symbol Q reversible in place of Q, and the expression 6 may be written as delta S is equal to Q reversible by T, which is equation 7. Further, as entropy is a state function, a small change in its value can be represented by ds. Hence, we may write ds is equal to q reversible by t, which is equation 8. Units of entropy. From the expression delta S is equal to Q by T, it is obvious that the units of entropy will be calories per degree if heat is expressed in calories. Further, entropy is an extensive property. It is therefore important to mention the quantity of the substance involved. It is usually expressed for 1 mole of the substance, hence, the entropy units are calories per degree per mole. If heat is measured in joule, the units of entropy will be joules per degree per mole. 2.6 Entropy change in a reversible process. Suppose a process occur under completely reversible condition, that is, the heat is absorbed by the system reversibly and the heat is lost by the surrounding also reversibly. If Q reversible is the heat absorbed by the system reversibly, then the heat lost by the surrounding will also be Q reversible. If the process takes place isothermally at the absolute temperature T, then entropy change of the system will be given as delta S system is equal to Q reversible by T, which is equation 1, and entropy change of the surrounding will be given by delta S surrounding is equal to minus Q reversible by T, which is equation 2nd. Hence, the total entropy change for the combined system and the surrounding will be delta S system plus delta S surrounding, which is 0, which is equation 3. Thus, we may conclude that in a reversible process, the net entropy change for the combined system and the surrounding is 0, that is, there is no net change in the entropy. 2.7 Entropy change in an irreversible process. If any part of the process is irreversible, the process as a whole is irreversible. Suppose that the total heat lost by the surrounding is Q irreversible. This heat will be absorbed by the system, but the entropy change of the system does not depend upon the heat actually absorbed, but it depends upon the heat absorbed reversibly, that is, on the quantity Q reversible. Thus, if the heat is absorbed isothermally by the system at the absolute temperature T, the entropy change of the system will be delta S system is equal to Q reversible by T, which is equation 1. Further, suppose that the loss of heat Q irreversible by the surrounding takes place infinitely slowly and isothermally at temperature T. Then the entropy change of the surrounding will be given by delta S surrounding is equal to minus Q irreversible by T, which is equation 2nd. The total entropy change for the combined system and surrounding will therefore be delta S system plus delta S surrounding, that is Q reversible by T minus Q irreversible by T. Now we know that the work done in an irreversible process is maximum work, that is W reversible is greater than W irreversible, which is equation 4. Further, as the internal energy is state function, the value of delta U is same whether the process is carried out reversibly or irreversibly. Hence, delta U is equal to Q reversible minus W reversible is equal to Q irreversible minus W irreversible, which is equation 5. Combining results of equation 4 and 5, we conclude that Q reversible is greater than Q irreversible, equation 6, and Q reversible by T is greater than Q irreversible by T, equation 7, and Q reversible by T minus Q irreversible by T is greater than 0 is equation 8. Combining these results with the result given in equation 3, we observe that delta S system plus delta S surrounding is greater than 0, which is equation 9. Thus, it may be concluded that in an irreversible process, the entropy change for the combined system and the surrounding is greater than 0. That is, an irreversible process is accompanied by a net increase of entropy. Since all spontaneous processes are thermodynamically reversible, it may be stated that all spontaneous processes are accompanied by a net increase of entropy. This is also one of the very common statement of the second law of thermodynamics. The result for the entropy change in a reversible process and that in an irreversible process may be combined together and put in the form delta S plus delta S surrounding is greater than equal to 0, where the sign equal to stands for the reversible process and the sign greater than for the irreversible process. The exact calculation of the total entropy change during an irreversible process, for example, when heat flows from a body B at higher temperature to a body A at lower temperature, when brought in contact with it may be carried out as follows. Suppose the heat lost by the body B is represented as Q irreversible. The flow of heat may be allowed to take place infinitesimally slowly so that it is absorbed by the body A reversible and isothermally at temperature T1, which may be represented as Q reversible. The entropy change of the body B will also depend only on Q reversible. Hence, entropy change of body B is equal to minus Q reversible by T2 and entropy change of body A is equal to plus Q reversible by T1. Minus sign indicates decrease in entropy while in positive sign indicates increase. So delta S total is equal to Q reversible into 1 by T1 minus 1 by T2. Clausius inequality. As discussed above, for an irreversible process, the result given in equation 9 may be written as delta S system plus delta S surrounding is greater than 0. So, delta S system is greater than minus delta S surrounding. So, we have delta S surrounding is equal to minus Q by T, and putting this value, we get delta S system is greater than Q by T. For small changes, the above equation may be written as ds system is greater than minus ds surrounding. So ds system is greater than dq by dt. So this expression are called Clausius inequality. These equations show that irreversible processes are accompanied by increase of entropy. This is further illustrated with the help of following two examples of irreversible process. First is spontaneous expansion. Irreversible adiabatic expansion. Suppose the system undergo irreversible adiabatic change, then dq is equal to 0. Hence, by Clausius inequality, ds system is greater than 0. That is, the entropy of the system has increased. Further, as dq is equal to 0, this means that no heat is transferred into the surrounding. Thus, ds surrounding is equal to 0. Hence, total entropy change ds total is equal to ds system plus ds surrounding is equal to ds system. But ds system is greater than 0. Hence, ds total is greater than 0. B. Irreversible isothermal expansion. We know that when a perfect gas expands isothermally, its internal energy remains constant, that is, Tu is equal to 0. Hence, according to the first law of thermodynamics, du is equal to dq plus dw, that is, dq is equal to minus dw. If the gas expands freely into vacuum, no work is done, so that dw is equal to 0. Substituting this in equation second, we gives dq is equal to 0. Hence, by Clausius inequality, ds system is greater than 0. Further, as dq is equal to 0, this implies that ds surrounding is equal to 0. Hence, the total entropy change as in above case, that is, ds total is greater than 0. Second is spontaneous cooling. Suppose heat is transferred from one system at a higher temperature T2 to another system at a lower temperature T1. If heat dq leaves the source and enters the sinks, so entropy change of the source is equal to minus dq by T2 and entropy change of the sink is equal to dq by T1. So total entropy change is ds total is equal to dq into 1 by T1 minus 1 by T2. As T2 is greater than T1, so ds total is equal to positive, that is, cooling is accompanied by increase of entropy. 2.9 Entropy change of the universe. Since all spontaneous processes occurring in nature are thermodynamically irreversible, these are accompanied by increase of entropy. Hence, it may be concluded that the entropy of the universe is continuously increasing. This result is sometimes taken as another statement of the second law of thermodynamics. Thus, the main idea of the first and second law of thermodynamics may be summed up in the following statement. The energy of the universe is constant, whereas the entropy of the universe is continuously increasing and tends to a maximum. 2.10 Entropy change for an ideal gas with change in P, V and T. Consider 1 mole of an ideal gas enclosed in a cylinder fitted with a frictionless piston. If an infinitesimally small amount of heat del Q reversible is supplied to the system reversibly and isothermally at the temperature T, then the entropy change accompanying the process will be given by ds is equal to del q reversible by T. And according to first law of thermodynamics, for an infinitely small process, del q is equal to du minus del w. If the process is carried out reversible, equation 2 may be written as del q reversible is equal to du minus del w. Further, if the work is restricted to the work of expansion, then minus del w is equal to p dv, where dv is the small increase in volume and p is the pressure of the system. Putting the value of del w from equation 4 in equation 3, we get del q reversible is equal to du plus p dv. On substituting this value, we get ds is equal to du plus p dv by T, which may be written as Tds is equal to du plus p dv. Now for 1 mole of an ideal gas, we know that Cv is equal to du by dt. So du is equal to Cv dt, where Cv is the molar heat capacity at constant volume, and for ideal gas equation we know Pv is equal to RT, so P is equal to RT by V, where V is the volume of the system at temperature T and pressure, and R is the gas constant. Putting the values Tu and P from equation 7 and 8 in equation, we get ds is equal to Cv dt by T plus R into dV by V, which is equation 9. If the volume changes from V1 to V2, when temperature changes from T1 to T2, then the entropy change accompanying the complete process will be given by integration of ds limits from S1 to S2 is equal to integrating Cv dt by T from T1 to T2 plus integration R dV by V from V1 to V2. Assuming that Cv remains constant in the temperature range T1 to T2, so equation 10 may be written as delta S is equal to Cv ln of T2 by T1 plus R into ln of V2 by V1, which is equation 11. This is an expression for the calculation of entropy change of 1 mole of an ideal gas accompanying a process when temperature changes from T1 to T2 and volume changes from V1 to V2. Further, for 1 mole of an ideal gas, we may write P1 V1 is equal to RT1 for the initial state and P2 V2 is equal to RT2 for the final state. On dividing these two equations, we get V2 by V1 is equal to T2 P1 by T1 P2, which is equation 14. On putting these values in equation 11, we get delta S is equal to Cv into ln of T2 by T1 plus R into ln of T2 P1 by T1 P2. Further, we note Cp minus Cv is equal to R. So putting this value in equation 15, we get delta S is equal to Cp into ln of T2 by T1 minus R into ln of T2 by T1 plus R into ln of T2 by T1 plus R into ln of P1 by P2. So delta S is equal to Cp into ln of T2 by T1 plus R into ln of P1 by P2, which is equation 16. This is an expression for the calculation of the entropy change of 1 mole of an ideal gas accompanying a process when temperature changes from T1 to T2 and pressure changes from P1 to P2. Entropy change of an ideal gas in different processes. So equation 11 gives the entropy change for 1 mole of an ideal gas when temperature and volume are variables. Similarly, equation 16 gives the entropy change of 1 mole of the ideal gas when temperature and pressures are variables. These equations are modified if conditions of constant temperature, pressure or volume are imposed. For example, first, if temperature is kept constant, that is, for isothermal process T1 is equal to T2, so equation delta comes delta S is equal to R into ln of V2 by V1 is equal to R into ln of P1 by P2, which is equation 17. Alternatively, these expression can be derived directly as follows, that is delta S is equal to Q reversible by T and minus W maximum is equal to Q reversible is equal to nRT into ln of V2 by V1 or equal to nRT ln of P1 by P2. Substituting the value of Q reversible and putting n is equal to 1 for 1 mole of the ideal gas, we may get the result given in equation 17. Second, if pressure is kept constant, that is for isobaric process when P1 is equal to P2. So delta S is equal to Cp into ln of T2 by T1, which is equation 21. Third, if volume is kept constant, that is for isochoric process, V1 is equal to V2. So delta S is equal to Cv into ln of T2 by T1, which is equation 22. Note carefully that all the expression derived above for the calculation of entropy change involve natural logarithm. Since logarithm table commonly used r to the base 10, in applying these formula, ln x has to be first replaced by 2.303 log x, where x is quantity like T2 by T1, V2 by V1, etc. Further note that if a gas expands reversibly but adiabatically, then for such a process Q reversible is equal to 0. Therefore, delta S is equal to 0. Entropy change during physical change, that is phase change. A change of phase occur in any one of the following cases. First, when solid melts, or conversely when a liquid freezes. Second, when a liquid evaporates, or conversely when a gas condenses. Third, when one crystallizes from change into another. When the change of phase commences, the temperature remains constant till the change of phase is completed. The heat evolved or absorbed during the phase change thus does not change the temperature and is therefore called latent heat. It is further termed as latent heat of melting, latent heat of vaporization, etc., depending upon the nature of the process involved. In general, if delta H is the latent heat and T is the temperature at which the change of phase occurs, the entropy change accompanying the phase change will be given by delta S is equal to delta LH by T. The entropy change delta S is termed as entropy of melting, entropy of vaporization, etc., depending upon the nature of the process. For example, we have first entropy of melting or fusion. So delta SF is equal to delta fusion H by TF, where delta fusion H is latent heat of fusion and TF is the melting temperature. Second, entropy of vaporization. So delta SV is equal to delta vaporization H by TB, where delta vaporization H is the latent heat of vaporization and TB is the boiling temperature. It may be mentioned here that the processes like melting and evaporation involve absorption of heat, which is taken as positive by convention of sign. Therefore, delta S for these processes is positive, that is, these processes are accompanied by the increase of entropy. On the other hand, the reverse processes like freezing and condensation involve evolution of heat, which is taken as negative. Therefore, for these processes, delta S is negative, that is, these processes are accompanied by the decrease of entropy. It may also be remembered that if the heat is measured in calories, the unit of entropy change are calories per degree per mole. If heat is measured in joule, the unit will be joule per degree per mole. Next is entropy change on mixing of ideal gases. Suppose at constant temperature N1, moles of an ideal gas 1 at initial pressure P1 naught are mixed with N2 moles of another ideal gas 2 which has initial pressure P2 naught. Suppose after mixing, the partial pressures in the mixture are P1 and P2 respectively. Now we know that at constant temperature, the entropy change of an ideal gas when its pressure changes from initial pressure P1 Pi to final pressure Pf is given by delta S is equal to R into ln of Pi by Pf mole inverse. Entropy change of the first gas when the pressure of N1 moles of the gas changes from P1 naught to P1 is given by delta S1 is equal to N1R ln of P1 naught by P1, which is equation 1. Similarly, entropy change of the second gas when pressure of N2 moles of the gas changes from P2 naught to P2 is given by delta S2 is equal to N2R into ln of P2 naught by P2, which is equation 2. Total entropy change on mixing the two gases will be delta X mixing is equal to N1R ln of P1 naught by P1 plus N2R into ln of P2 naught by P2, which is equation 3. If P is the total pressure of the mixture, that is P is equal to P1 plus P2, and X1 and X2 are the mole fraction of gases 1 and 2 in the mixture, then by Dalton's law of partial pressures, P1 is equal to X1P and P2 is equal to X2P. Substituting these values in equation 3, we get delta X mixing is equal to n1r ln of p1 naught by x1p plus n2r into ln of p2 naught by x2p, which is equation 4. Taking the simplest case in which each gas is taken as the same initial pressure and after mixing, volume of the mixture is the sum of the initial volumes, that is V is equal to V1 plus V2. The final pressure of the mixture will be nearly same as initial pressure of each gas, that is P1 naught is equal to P2 naught is equal to P. Then equation 4 is simplified to the form delta S mixing is equal to minus N1R ln of x1 minus N2R ln of x2. That is delta X mixing is equal to minus R into N1 ln x1 plus N2 ln x2, which is equation 5. For a mixture of number of ideal gases, equation 5 can be generalized to the form delta S mixing is equal to minus R summation of Ni ln of xi, which is equation 6. To calculate the entropy change for 1 mole of mixture, divide equation 5 by N1 plus N2, we get delta S mixing is equal to minus R into x of ln x1 plus x2 into ln of x2, which is equation 7, which can be generalized to the form delta S mixing is equal to minus R summation of xi ln of xi, which is equation 8. From the above equation, we may conclude that first, delta S mixing is independent of temperature. Second, as xi is less than 1, so delta S mixing will always be positive, that is, mixing of gases is accompanied by increase in entropy. 2.13 Physical significance of entropy, that is, measure of disorder. An examination of the various processes which are accompanied by a net increase of entropy shows that they are associated with an increased randomness of distribution. For example, first, the melting of solid is accompanied by a net increase of entropy, and at the same time, we know that the molecules, atoms, or ions in a solid have fixed positions and they become free to move about in the molten state. This is expressed by saying that there is no disorder among the molecules, atoms, or ions in the solid, but the disorder set in when the solid changes into liquid. In other words, it is stated that the randomness has increased. Second, the vaporization of liquid is accompanied by a net increase of entropy, and at the same time, the disorder or the randomness also increases because the molecules of vapor are more random than the molecules in the liquid. Third, heating a magnetized iron needle demagnetizes it because the molecules of the magnetized iron needle, which were oriented in a particular fashion, lose the order on heating and becomes disorder, that is, randomness increases. Fourth, all spontaneous processes like diffusion of gas, flow of heat from the hot end to the cold end of an iron bar are accompanied by a net increase of entropy as well as increase of randomness or disorder. For example, in the phenomenon of diffusion, the two gases which are separated initially get mixed up in the random manner. Similarly, in the flow of heat, the electrons present on the hot end and having higher kinetic energy rush to the cold end, thereby making the distribution more random. Hence, it may be concluded that entropy is a measure of randomness or disorder of the system. This concept may be further understood with the help of following example. First, in a college, when all classes are being held, all the students are sitting in their respective classrooms and the disorder is minimum. As soon as the bell goes, the students of different classes come out to go to the other room and thus get mixed up. In other words, the disorder or the randomness increases. Second, in the game of hockey or football, to start with, all the players take up some definite position and thus are said to be in order. As soon as the game starts, the players start running and thus they are said to have an increased randomness with increase further as the game catches more and more momentum. Thank you.